Our final speaker of the day is Carina Prunkl from the University of Oxford, who's going to give us a survey of resource theories and thermodynamics.
Thanks very much. It's a pleasure to be here, in particular because there are not that many conferences on resource theories that also, that are organized by philosophers and that involve the collaboration between physics and philosophy, and so it's a great opportunity to be here. So you might have noticed that in the abstract I said I would be talking about the axiomatic thermodynamics and how it compares to resource theories. And when I was doing research on the project, when I was starting with the project, I realized that there already exists work on the topic. So there already exists a paper by Weilenmann who is doing exactly the same thing. Nevertheless, I think I still think it's worthwhile talking about it. So I will be discussing some of their results, in particular because axiomatic approaches to thermodynamics are quite popular among philosophers. They are said to give a clear mathematical foundation for entropy, and other philosophers are quite skeptical of the idea that the von Neumann entropy is the correct quantum mechanical generalization of the thermodynamic entropy. So by showing that these two are that resource theories that give us the von Neumann entropy are structurally similar or consistent with the Lieb and Yngvason axiomatic approach to thermodynamics, might hopefully persuade them a bit to reconsider their opinion on the von Neumann entropy. Now, another thing that happened, so when I was researching this, is I stumbled upon claims like the following by Lydia Del Rio. She said, resource theories have advanced our understanding of fundamental physical principles, such as the second law of thermodynamics. And then I wondered, have they? Is it clear? And if so, in what way? So I decided to use the opportunity of having an audience that consists of philosophers and physicists working on the topic to probe this claim that resource theories actually do give us something new about the fundamental physical principles, such as the second law of thermodynamics. So I'm going to split my talk into half. In the first part, as promised in the abstract, I'm going to talk about Lieb and Yngvason's approach to thermodynamics and compare to the resource theories. In the second part, and hopefully this is going to also be a good way to start the general discussion afterwards, I'm going to talk about the contributions of resource theoretic approaches to the foundations of thermodynamics. So I'm going to divide them into two parts, into the scope of thermodynamics and entropy, but I will be talking more about this when I get there. Okay, part one: resource theories and axiomatic thermodynamics. So the idea of axiomatic thermodynamics is to come up with a set of axioms, and from those to derive to show that there exists a unique entropy function that's monotonic, additive, and extensive. Now, the motivation by Lieb and Yngvason is the following. So they say there are two aims to our presentation. One is frankly pedagogical, i.e. to formulate the foundations of the theory in a clear and unambiguous way. The second is to formulate equilibrium thermodynamics as an ideal physical theory, which is to say a theory in which there are well-defined mathematical constructs and well-defined rules for translating physical reality into these constructs. So one of the beauty of these axiomatic approaches are that they're very precise, they're mathematical, rigorous, as we will see. Now, the key features are they're only concerned with the phenomenological with the phenomenological entropy, and they're also concerned with systems of a certain size. So they're looking at macroscopic systems. They explicitly rule out systems in which fluctuations become of importance, and they rule out systems for which gravity becomes non-negligible. Also, they're only talking about equilibrium thermodynamics, so they're considering a state space of equilibrium states. as opposed to considering non-equilibrium states. They have added that to their formalism a few years later, but I think it's going to, I'm not going to talk about the non-equilibrium cases. Now, at the center of the Lieb and Yngvason approach is the notion of adiabatic accessibility. So they're considering an order relation on a set of equilibrium states, and they're looking at which states are adiabatically accessible from each other. So the idea is that, here they define the notion of adiabatical accessibility in an operational way. They write, a state Y is adiabatically accessible from a state X in symbols. You say either Y is adiabatically accessible by X, or you can also say X precedes Y. If it is possible to change the state from X to Y by means of an interaction with some device consisting of an auxiliary system and a weight, in such a way that the auxiliary system returns to its initial state at the end of the process, whereas the weight may have risen or fallen. So you perform a thermodynamic process, and at the end, the only thing that might have changed is the weight, which could have risen or fallen. Now, beneath they write the notion of adiabatic equivalence. So if X precedes Y and Y precedes X, so basically if Y is adiabatically accessible by X and the state X is adiabatically accessible by the state Y, then we say that these two are adiabatically equivalent. Now this looks really scary, but it actually isn't that. Maybe given the time of the day, it's even scarier. So these are the axioms Lieb and Yngvason then postulate that will give rise to a unique entropy function. So I will just very briefly go through them. The first one is reflexivity. So a state has to be adiabatically equivalent to itself. Then it's transitivity. Again, if we perform two adiabatic processes, one after the other, then the state of the system at the end should be always also adiabatically accessible by the state at the beginning. Then there's consistency, which basically just says that when we have compound systems, then the compound system, the final state of the compound system has to be adiabatically accessible by the initial state of the compound. Then there's scaling invariance, which is given here for any lambda larger than 0, and X precedes Y, then lambda X precedes lambda Y. There's splitting and recombination, which just means that you can take your box of gas and you can split it into parts and you can put it back together. And then this is adiabatically equivalent. And then there's stability, which again just captures the intuition that your system is stable against small perturbation. And then there is the comparison hypothesis. Now this is really not an innocent hypothesis. In fact, they show this hypothesis from further axioms later. It states that the comparison hypothesis holds for a state space gamma if all pairs of states in gamma are comparable. Now, to be comparable, it means that if X and Y are comparable, then either X is adiabatically accessible from Y or Y is adiabatically accessible from X. This is quite a strong assumption, and we'll come back to this in a bit. Now, they then show that there exists a unique entropy function, and this is called the entropy principle. So they say there is a real valued function on all states of all systems, including compound systems, called entropy, and denoted by S such that it's monotonic. So X and Y, when X and Y are comparable, then X precedes Y if and only if the entropy of X is smaller or equal than the entropy of Y. And it's also additive and extensive. I'm not going to read that out because I should hurry. Now, here again, they show that if two states are adiabatically equivalent, then the entropy of these two states ought to be equal. And in particular, if there's so the double, like these double squiggle means that x precedes y, but y does not precede x. So it's just a one-way street, so to say. Then the entropy of x has to be smaller than the entropy of y. Okay, so this is all I want to say about the Lieb and Yngvason approach. I think you get the idea. There is a set of axioms, and this set of axioms establishes an order relation that provides us with a unique entropy function. Now, for the resource theories, I'm going to briefly repeat the very basics, but Rob did a good job in explaining them yesterday, and so I don't want to dwell on them for too long either. But most resource theories, probably all resource theories, have three basic ingredients. So there is a set S of free states, which are the states that are freely and abundantly available to the experimenter. Then there is a restricted set C of available quantum operations. And then there is a set R of resources, which consist of states that cannot be created by S and the set of quantum operations alone. Now the aim is then to determine which states are accessible from each other given these restrictions, given the restricted set of quantum operations. Now in particular, there is a resource theory of noisy operations where our free states are the maximally mixed states, our operations are the compositions within ancillary system in a maximally mixed state. They are the unitary transformations on system and ancilla, and they are also the tracing out operations. Now the resources are all other states. Now, in order to, as you might have noticed, like these are very general theories, and the Lieb and Yngvason approach we saw earlier was very restrictive in the conditions that we imposed on the set of states. And so Weilmann et al. When they tried to show the structural similarities between the Lieb and Yngvason and the resource theory of noisy operations and of athermal operations, they had to put on some restrictions on their set of operations as well, which are more compatible with what we know from thermodynamics, from phenomenological thermodynamics. And so they restricted the operations to the composition with an auxiliary system in an equilibrium state. So they define the notion of an equilibrium state, and they also demand that the ancillar at the end of the process has to go back to its original state. Now, I probably won't talk about this in detail. Actually, I won't. But they come up with an order relation. Here, it's similar. The notation is very similar to the Lieb and Yngvason one, the majorization that also defines an order on the set of equilibrium states, and they then show that the Lieb and Yngvason axioms hold for this order relation, for this majorization relation here. Now, and they then show that there exists also a unique, and once we have these restrictions on our set of operations, on our set of states, then there does also exist a unique entropy function for equilibrium states that coincides with the von Neumann entropy. So this is basically their way of showing, well, look, we have shown that from a within a resource theoretic framework, we can also derive the von Neumann entropy. Now, and I think among physicists, it's quite an established fact that the von Neumann entropy coincides with should be considered like the thermodynamic entropy in the philosophy community. This is a bit debated by some people, not by myself. So when we want to, so let's compare them. The Lieb and Yngvason approach, we had the order relation with certain properties, which were characterized by a set of axioms. And it was shown that this is equivalent to the existence of a unique entropy function. Now, as I said earlier, there is Lieb and Yngvason applies to macroscopic systems. It deals with the phenomenological entropy, and as opposed to the resource theories, which are formulated in terms of operations, in terms of agents that can perform different operations and interactions with a system. In the Lieb and Yngvason approach, we don't have such agents. So I wrote on first sight because even though they're interested in the structure of the state space and in this order relation. Implicitly, they still need agents or people who bring their system out of equilibrium. And David mentioned that earlier in his talk. That yes, sure, if our state space just exists, consists of equilibrium states, we're gonna have to do some interventions at least in order to get our system into different states. Now, the resource theories, on the other hand, they consist of a set of free state, a set of operations, and the resource states. And this also defines an order relation with the restrictions that were given before. This gives us a unique entropy, which also fulfills the axioms. And but it's formulated in terms of quantum systems. It's explicitly operational. It does include the notion of an agent. And much more importantly, it is much more general than the Lieb and Yngvason approach. So just to sum these things up, the Lieb and Yngvason approach has much stronger assumptions than the resource theoretic approach. So the resource theories give us a family of entropy functions, whereas the Lieb and Yngvason approach, some of them might argue, I think Owen argues that the assumptions they put on their systems are way too strict, and we should relax them a bit. Now, resource theories give a good way of relaxing them. Now, I think it's still good. It's somewhat of a consistency check that the resource theories are able to recover the Lieb and Yngvason framework and are able to recover an entropy function that does fulfill the axioms of Lieb and Yngvason. But of course, there are very different motivations behind the project. Okay, this is all I want to say. I'm happy to talk more about this later in the Q&A, or also to receive suggestions, whether you see some more similarities or differences. But now, part 2. Have resource theories advanced our understanding of thermodynamics? Now, I'd like to see some hands. Who thinks yes? 1, 2, 3, 4. Okay, who thinks no? Really? Who is not sure? Okay.
The conference on resource theories and thermodynamics might not be the great event themselves.
Yeah, I agree. Okay, so when I wonder about thermodynamics, there are two things that puzzle me in particular. One of them is just the universality of thermodynamics, the universalities of the laws of thermodynamics, or the thermodynamic-like behavior we see in nature. Here is a quote by Einstein, who writes, "Thermodynamics is the only physical theory of universal content, which I am convinced that within the framework of applicability of its basic concepts will never be overthrown." Now, another quote which I like very much is Peter Atkins, who warns his students in his book, The Four Laws that Drive the Universe. Do not think that thermodynamics is only about steam engines. It is about almost everything. So there are many things here to discover. Like, what is almost everything, and what does it mean to be about almost everything? So this is something that puzzles me, and in particular. Thermodynamics seems to pop up in all these different areas of physics that are sometimes not only physics, but also in the special sciences. So, for example, obviously it occurs in statistical mechanics, as we saw, through this conference, or as well known. Quantum information theory uses thermodynamics and entropy. Now, there exists a field called black hole thermodynamics. Again, some philosophers are skeptical. Many physicists will just say, well, of course, there's thermodynamics of black holes. Then the laws of thermodynamics also appear in chemistry, in biology, in the special sciences. Now it's arguable whether in economics whether this is thermodynamics or something completely different. But we have these laws that pop up everywhere. So why is that? So this is one of the puzzles one of the things that puzzles me. Another one is, what is entropy? Now here is a famous quote by von Neumann. I'm not going to read. I didn't put in the whole quote because everyone knows it. But von Neumann famously told Shannon that nobody knows what entropy is. And yes, and when we look at all the list of different entropies, it becomes clear that it's not so easy to pin down what entropy is, and they might act like all these entropies might not be the same, or probably are not the same, or might refer to different things. And then, of course, there's also the question, how do we interpret entropy? So do we interpret it as means relative concept? I guess most people here are in favor of that, or as ignorance. Some people here are in favor of that, information, or as disorder and spread outness, or as a property of the microstate or the macrostate. So there are all these different interpretations, and this is just like one way of putting them all of putting some errors, and I left out half of the errors as well. I mean, it just becomes very complicated to figure out what we mean by entropy. And maybe, and different concepts suggest, different entropies suggest different interpretations. And then, of course, given that resource theories have been developed in the context of information theory, one thing that I also ask myself, do resource theories give us any indication that we should interpret entropy as information theoretic? So, this is another thing I want to explore. Does it mean, if we consider resource theories, if we consider even a means-relative approach to thermodynamics, does it commit us to an epistemic view of entropy or an information theoretic view of entropy? Now, and then of course these two aspects are linked. So it's quite likely that if we solve one, we solve the other. But who knows? Okay, so I summarize these things in all these questions into three main questions I want to ask, and hopefully we can have a discussion about them later. So, does a means-relative or control-theoretic approach to thermodynamics commit us to an anthropocentric information-theoretic view of entropy? So this was the last question I was asking. I'm kind of going backwards. Now, related, does the success of resource theories commit us to an information theoretic understanding of entropy? Now these, the first two are clearly linked. And then the third one, what are the implications for the seeming universality of thermodynamics? Can resource theories tell us something about that? Now, so I'm going to start with the first question. Whether means-relative or control-theoretic approach to thermodynamics does us commit to an epistemic view of entropy? And to do so, I'm just going to briefly motivate again the means-relative view that was already presented by Wayne yesterday, but some people weren't here, and I think it's also a good thing to have these things fresh in the back of your mind. So, we have the orthodox second law, which states that heat cannot pass from a colder to a warmer body without compensation. Now, as we saw yesterday, where Maxwell, on small scales, the orthodox second law is violated all the time. So there are two options we have now. So either we say, and this is what Maxwell did, the second law is a statistical rather than a mathematical truth, and if we consider, so basically, practically, it's never violated, in particular not for macroscopic systems. The other idea is to read the second law as a probabilistic statement and say, well, the second law forbids the reliable conversion of heat into work from a single reservoir by a cyclic process. And this is made precise by the notion of the expectation values. Now, note the difference between these two options. Whereas, and this is what David was getting at with his two demons as well, I think, the probabilistic second law is a change. We amend the content of the second law. We make it. We change the statement into the second law. It forbids the reliable conversion of, consistent and reliable, I think, conversion of heat into work from a single reservoir. Whereas the statistical second law refers to a practical impossibility. So these are clearly distinct and So I want to zoom in a bit more on the practical impossibility, because this is how we motivated the means relative approach yesterday, or how Wayne did it. Maybe something I should say. There's a big question whether we can still talk about the phenomenological entropy when we're amending the second law. We're including the notion of probabilities and expectation values, because these are things from statistical mechanics, and not from phenomenological thermodynamics. Okay, so for the means relative approach, so we saw that that the statement that it is impossible to perform a cyclic process whose sole outcome is the conversion of heat into work cannot be a nomological impossibility. So it cannot be something that's demanded by our laws of nature. Instead, it's a practical impossibility. And I think the moment we start talking about practical impossibilities, now this is where we start thinking about means and agents and beliefs, or maybe I should have said a knowledge rather than means and agents. So because you could say, well, somebody with more information, with more knowledge about the system is able to extract more work from it. So we have Maxwell here who makes this link between means relative and anthropocentric in a way. So he says confusion, he means heat, like the correlative term order, is not a property of material things in themselves, but only in relation to the mind which perceives them. So he puts the agent into the picture, as Wayne pointed out in his paper. And then Jaynes later went even further by denying the physical nature of entropy. So he said the strong contrast between the physical nature of energy and the anthropomorphic nature of entropy was well understood by Gibbs before 1875. Now I think they're being too quick here. I think adopting a means relative understanding, I'm calling it means relative for lack of better words, but adopting a means relative understanding of thermodynamics does not require us to have an epistemic notion of entropy or thermodynamics. Why not? So entropy in the phenomenological entropy is a property of the macrostate. So here the macrostate is given by variables like x1 to xn. Now it is true that an agent, so think about the Gibbs paradox, we have two gases where the molecules slightly differ from each other, and an agent who knows about this difference is in principle able to extract work from the system, whereas an agent who doesn't is not. So agents can disagree on the description of the macroscopic description of one and the same system, but I don't think that this makes entropy epistemic. Well, why not? First of all, you might wonder, well, entropy is defined relative to this kind of arbitrary description. Doesn't that make it anthropocentric? I say, well, not really, because we have in physics we have quantities that are defined relative to other things all the time. I mean, from thermodynamics, the notion of equilibrium is defined relative to the macrostates, or to a given set of variables. And also in other parts of physics, we have kinetic energy, for example, that's defined relative to a given reference frame. Now, this doesn't mean that these things are unphysical. If I'm driving a car and I bump into another car, then the dent the dent will happen no matter whether whether I'm looking at my reference frame or the reference frame of the car that I accidentally bumped into. So I think just the fact that entropy is defined relative to things is not it doesn't require us to call it epistemic. I think that's pretty clear. I think this is stating the obvious. I'm just putting it out there. Now then you might say, well, but different agents might disagree on how much different agents can assign different entropies to one and the same system. That's because one agent knows more than the other agent. But you don't need to have this kind of rhetoric. You could also say, well, they're just different choices of variables we're having. Now, in fact, it's just a different choice of description. You can consider entropy to depend on the level of description you're choosing to describe your system. You don't have to bring in knowledge to do that. Okay, so I have 5 more minutes now. So does a means-relative controlled theoretic approach to thermodynamics commit us to an anthropocentric theoretic view of entropy? I don't think so. And as a consequence, does the success of resource theories commit us to an information theoretic understanding of entropy? I don't think so either. And the first point was just made. I don't think that a means-relative view of thermodynamics commits us to an information theoretic or an epistemic view of entropy. And furthermore, I think another indication is that there exist alternative derivations of the phenomenon entropy that have nothing to do with information theory. And one of them was given by Owen this morning, where he showed that we can derive the phenomenon entropy just by basic quantum mechanics and by putting a set of restrictions on the operations. Or by just choosing there are certain operations that are given to us from thermodynamics. Now, so I think here it's no as well. So what are the implications then for the seeming universality of thermodynamics? Here I think resource theory probably fares best because it just shows up this really lean, it just shows up how these monotons pop up and what you need in order what you need to put in order to get these different entropy functions out. Now, I put this first point here because just to mention again that some people might disagree with the fact that we can associate probability distributions or mixed state with actual thermodynamic states in the first place, but yeah, never mind that. So I think resource theories are incredible when it comes to deriving thermodynamic, or when it comes to showing why some things have like this thermodynamic behavior that we observe. On the other hand, it's also a question whether they're in some sort demystifying the second law, or whether we actually believe that. I mean, the second law has been puzzling people for a century. Like, do we really think that now resource theories are the solution to this and provide us with a satisfactory answer? I'm quite interested to hear what you think about that. Now, I'm going to wrap up. So I said that by now it's probably clear that resource theories are a lean and powerful framework that are incredible at making predictions about which transitions between states given a set of operations are possible and are impossible. And they do capture the control theoretic aspect of thermodynamics, or the means relative aspect of thermodynamics. And maybe I should mention that why I'm a bit skeptical of the whole idea of means relative, because when we assign entropy to the sun, for example, or other objects, we don't really have the means to do operations with the sun. So I think the control theoretic, the term probably also suffers from similar weaknesses, because we also don't have any control about the sun. So I think we should be a bit more a bit careful and maybe choose a terminology that captures better what's going on. I don't think that a means relative or control theoretic understanding of entropy commits us to an information theoretic reading of it, but I do think that resource theories may explain some of the universal aspects of thermodynamic-like behavior. So thank you very much.
Thank you. Questions?
First, I want to agree with something you said and offer you yet another example. Right? So you asked a general question, does the fact that something is means relative, and in particular all resource theories are essentially just trying to formalize the notion of what means is this conversion relative to. So all resource theory sort of has that notion of means relative to. Does that imply that the functions that measure the resource are somehow epistemic or representing epistemic things? I think the answer is clearly no, because the resource theory framework is so broad, it can capture many other things besides information theoretic objects. So one of my favorite examples is not even an example from physics, but it's an example from mathematics. So you can define a resource theory as a kind of proof theory in mathematics, where you can ask, suppose I give you for free compass and straight edge constructions. So you want to make anything you make with a compass straight edge, that's free. And now we're going to ask the cost of any other geometric construction that I can't do with a compass and straight edge. And so relative to compass and straight edge, I can ask, for example, does the ability to trisect an angle, is it more or less or equally powerful to the ability to square the circle? All right, under the framework of compass and straight edge. So can I convert trisecting an angle to squaring a circle using compass and straight edge? That's a resource theory. And the answer in that case happens to be yes. Those are equivalent resources relative to the means of compass and straight edge. But does that mean that the geometric constructions are somehow epistemic? No, not at all. It's just not that category of theory today.
But you still think that the resource theories here are give us an indication that we should consider entropy to be understood in epistemic terms, no? This is how I understood you yesterday.
Well, so the argument in the talk I gave yesterday was not, by virtue of the fact that I can characterize these as resource theories, measures of athermality and measures of asymmetry are necessarily epistemic, but rather the fact that there's this bridge principle which shows that every measure of athermality and every measure of asymmetry is ultimately a measure of information carrying capacity in disguise. That's what proves that they're epistemic.
Proves that they're epistemic?
Yes.
Uh-huh.
That they're measuring, that they're an information theoretic notion. So if I presented it differently, would it have had more impact? So suppose I said, and this is historically a little bit how it happened, that people studied asymmetry theory and athermality without necessarily being committed to this bridge principle I described, right? That was a discovery, right? But you could develop those theories without ever making a connection to information theory. So as a purely mathematical problem, you could say, I've defined a measure of athermality. It's any scalar function that's not increasing under thermal operations. And if I was a great mathematician, I might say, and here's the entire class of functions that satisfy that constraint. I can characterize them for you. In the case of noisy operations, it's all the Schur concave functions. Mathematicians have studied those, and so we just say that there they are. And you might look at that and say, well, who knows if that's measuring information or not? Who knows? But then you notice that the resource theory of information, if I try to encode a bit of information, say 0 always gets encoded in the thermal state, 1 gets encoded in some quantum state of your choice. And I ask, what's the partial order over all those encodings under data processing? And I ask, what are monotones relative to that? And I find I get exactly the same set of functions. They're exactly the same. That strikes me, is it a great coincidence that the resource theory of information generates exactly the same functions as the resource theory of athermality? I don't think so. I don't think it's a coincidence. I think it's because athermality ultimately is about the information carrying capacities of the system. And so, to my mind, if anyone wants to say they're not, they really have to say, explain that coincidence. Why is it that every measure, not just the entropy, but there's an infinite number of them, is a measure of information?
David.
I mean, in some ways, this is reinforcing some of your worries about the term means relative. I mean, here's a way of sort of putting my aspect of the concern this way of putting it. If I take your example of the sun, for instance, if I want to work out what's the entropy density of the sun, the way I calculate that is I just say, okay, I know the mass distribution. I've got a model that gives me the mass distribution of the sun, and then I just have a formula that says work out the canonical state for a given energy density, for a given particle number density, and then do rho log rho of it, and that's the entropy, or work out the addition function or whatever. So, I mean, it might be that there's some story along the lines of, well, all of that in some way tacitly relies on the salient dynamical processes going on in the sun. And that might be reason enough, but at least if we're trying to capture the notion of entropy that's being used if you're doing nuclear astrophysics, or any a number of other examples you could pick where we're not in the business of manipulating the system, then it doesn't feel as if there's a great deal of room for manoeuvre in deciding what the particular entropy is going to be. And I take that as being in support of the sorts of cautions you have there.
Thanks.
Go ahead, yes.
Okay. I had a question about the first part of your talk concerning differences between the Lieb-Yngvason and so one of the differences you mentioned was this agent, appearance of agents in the resource theory, but not. Right, you said that no agent was present at first sight in the Yngvason approach. And I take that to mean that they're considering an order relation which is not about whether I can sort of make X turn into Y, but rather something like X can go to Y.
Yeah, in principle,
naturally, or something like that. Is it possible in nature for X to go to Y if we're imagining that it's maybe not X versa? So I hear this distinction being made frequently, and it's usually presented to me as a kind of criticism of the resource theory approach, as, oh, that's a very anthropocentric approach, that's about what agents can do, I don't really care about what agents can do, I care about what can happen in nature, and therefore I'm skeptical of the pertinence of any of that to what I'm actually interested in, because it's just too wedded to humans and what they can do. And so I think that position is mistaken, and here's why. So I'm just wondering if you agree or not, which is, if you ask the question, can I engineer a machine? Give me very specific restrictions, like you can only do thermal operations or whatever, but nothing else, right? So I can do anything I like. Can I engineer a machine that would take X to Y? And if I find out all the transitions that are possible, all the transitions that are impossible, under the assumption that I can, no restriction besides thermal operations, so I can engineer anything I like, then that clearly implies whether it's possible to happen naturally or not. So if I can't engineer X to turn into Y, it can't happen naturally either. So the resource theory approach seems to be stronger to me than the non-resource theory approach, because it asks the questions, if you could really do anything in this restricted class, could you make it happen? And when you get a negative answer there, then you don't have to talk about what the initial conditions of the universe are. Could it happen for those? You know it just can't happen according to the laws of physics. So to my mind, there's a sort of logical implication from the bad anthropomorphic version of the question to the good, can it occur naturally version of the question. So that's why I feel like those kinds of fears are unfounded.
Yeah.
What do you think?
I don't know. I think the two approaches have just very different aims. It's like if you're more interested in what you can do with a thermodynamic system, then of course this operational or this agent operational approach to the means relative approach to thermodynamics makes more sense. But I think from the laws of thermodynamics themselves, and I think this is also the case for the Lieb and Yngvason approach, we can't really decide which one is the right one. So whether it's impossible, right? Whether it's like an actual impossibility, or whether it's a practical, like an engineering, restrictions on our engineering capacities or on our on other capacities. I think you just can't read it out of the second law. I think you could go either way. So I see how Lieb and Yngvason might, for example, just not be interested in what you can or you cannot do, but what is in principle possible to do.
But I think you missed my point, that in the resource theory approach, we're not saying what can I engineer with this screwdriver and this much money and so forth. We're saying what does the laws of physics allow us to engineer in principle? what could a civilization 1,000 years from now with better technology engineer? So when I prove that something can't be done under thermal operations, it's in that sense that it cannot be done in principle, no matter how much engineering sophistication you have. And my point is that once you realize that that's the case, then if you can't engineer something in that sense, it can't occur naturally either. Because it could be that the universe evolves and happens to generate a machine that extracts work and stuff. Typically you need natural selection in life and engineers to actually build it, but it could occur naturally. But the point is that if that does occur naturally out there, it's still not going to do any better than something that does the best you can by the laws of physics. So in that sense, it's putting limitations on what you can ultimately engineer in principle is putting limitations on what can occur naturally. You see what I'm saying?
No, I see your point. I think I'm going to have to, I don't know, I have a suspicion here, but I think I'm going to have to think a bit more about this to put my finger actually on what you're doing. Like, it seems to me hard to believe that there is actually such a preference in the theory for well, I don't know. I'm not going to say anything now. Let's talk later about it. I'll think a bit more about it. Thanks. Yeah.
Is that a finger, Wayne?
No, he has a finger. I have
Okay, go ahead.
Well, it's important that way of thinking about it. Suppose I want a mechanism for generating jets from galactic nuclei. If my purported mechanism is entropy decreasing, I can be pretty sure I made a mistake somewhere there. Whatever mechanism the galaxy is, whatever mechanism the galaxy is using to throw organised energetic jets into space, it's going to have to be doing it in some way that increases the entropy in the accretion disk or something.
I just want to. This is related to that point. So, the business about things being means relative. If I have a very general framework, the way the sort that say David and Rob were sketching, then I can get different theories depending on what means operations I allow in the theory, and you could have a theory of means relative concepts in which you're allowing operations any unitary, right? Or which is of course ridiculous from an engineering point of view, but there's a well-defined theory in which those are the operations that you can do. And I think there's a danger in thinking that when we talk about things being means relative, that we're talking about that's what we can do today or something like that. And this comes up also on the interventionist account of causation. People talk about an intervention on certain variables while holding others fixed. And one objection people say was, well, we want to talk about the causal effect of a volcano eruption on the climate. And we can't engineer a volcano eruption at will. But I think what Rob was saying is right. That's an engineering problem, and it's just not the case that there is no conceivable process that we could count of as intervening on the volcano eruption. Is just that it's beyond our current technology. So, and similarly with the sun, our ability to manipulate it is limited, but one can imagine machines in which it's put in a certain magnetic field and this magnetic moment is being manipulated and things like that. And those are very, I think we have an idea of the sorts of manipulations that are not in principle beyond the ability of some possible agent. And then, as David pointed out, there are things to do and there's things that just violate some very fundamental principles that would be beyond the ability of any possible agent, no matter how sophisticated.
David has a figure, but Carina, did you want to comment on that first?
No, I think I'm agreeing with what Wayne says.
Just a slight notion of caution. I guess if I had my science fiction goals on, I could imagine civilizations that manipulate stars or galactic cores or something. But we use thermodynamics in sort of early universe baryogenesis in a context where I find it extremely unlikely that it's even in principle physically possible to have agents who are actively manipulating the universe, that situation. So we don't want to just rely on that pure technological advance. We need to have a somewhat broader modality for that.
Yeah, Mike.
It's helpful to think of it in terms of the phrase means relative. Do we need to use that? Can we just say?
Sorry, can you please say that?
Rather than use the term means relative, can you rather just say, essentially what people have said in the past couple of days, a resource theory is a theory where you conditionalize upon a set of free states and a set of operations. And relative to these free states and set of operations, you have such and such a theory.
Yeah.
And you can talk about it in terms of means relative. Like, that's not necessary. That's what's essential. It's just that your theory is conditional upon these things that you optimize it to.
Yeah.
And
Yeah, I also realized probably, it's also clear, of course, that agents don't need to be human, right? They could be anything, basically.
Point on when you talk about it. It's interesting that one criticism from the other side that people make of resource theories, if you speak to an experimentalist, they will say the set of restricted operations you assume is, just a theorist's dream that you could do all unitary. What I want is, a set of restricted operations that characterizes what I can actually do in the lab today, and come back when you've got that resource theory, because that's the one that'll be useful to you. The framework accommodates both extremes.
Yeah, that's true.
All right, let's thank Carina.
Thank you.
So we're going to come back for a general